again. So while we will give the Willie, while we will give the director's discussion at the bottom, so we will start at the moment. So, dear colleagues, good afternoon, and thank you very, very much for taking the time off your very busy schedules to another edition of our webinar. Today, we have a very, very special guest from Jülich. He is Professor Albert Meulenberg, and he belongs to the Institute for Energy and Material Devices, IMD2, where we are currently doing collaboration. And so he is the professor with whom we are doing the collaboration, where I am particularly doing collaboration with. And today he will be talking to us on the recent development in ceramic membranes for gas separation and reactors. So Professor Meulenberg, I think you don't need any special introduction. You're already at Homeroom. You have visited us now, I think twice already, and we know you here very well. And I think your profile speaks for himself. So please, you have the floor.
Yeah, thank you very much, Kwati, for your invitation first, and also to Hiroshige and Tatsumi. I have to mention that we was renamed 1 month ago. Our old name was I²CNER. Maybe some people know us under this name, but since 1 month we have a new name. Yeah, good morning, everyone, or good afternoon. We have here 9 o'clock in the morning in Germany, and the presentation I give today, I was asked 2 weeks or 3 weeks ago in the International Conference on Inorganic Membranes to give a plenary lecture and to give an overview about the field of ceramic membranes. And I in principle modified a little bit this talk, which I also give today for you. And so I want to give also an overview about new research directions. And so that means I have a lot of different topics, but I will not to go too deep into all of these topics, only in some of them. So the first of all, I have to go to the next slide, sorry. So the question is, what is a membrane? And there is a definition in literature, and it says a membrane is in principle a layer which enables the separation of 2 different fractions from each other. So we are concentrated on gases here, but that is also for liquids or for solid components. And I was inspired to explain this by Professor Jürgen Caro, and he has a very nice explanation what is a membrane. So in principle, you start with a fraction of separation, that's called feed. This feed is distributed to a membrane, and then the retentate is, after passing the membrane, still there, and the permeate is on the other side of the membrane. I have to mention that there was no harm of the ducts. The ducts were saved after making this picture, Jürgen Caro said to me. So yeah, where is the application of such membranes? And in principle, you can classify the membranes by the pore size. So at 0 nanometer, that means dense membranes are ionic conductors. They have in principle no pores in the system. And then we have the so-called microporous membranes, which range between 0 and 1 nanometer in pore size. And then we have membranes above 1 nanometer, which are used, for example, for separation of blood cells, bacteria, viruses, or proteins. I have to mention that all what is above 1 nanometer in pore size is already commercially available. So I want to concentrate, therefore, today on the separation of gases and pervaporation. That means somewhere in the area from 0 nanometers, so the dense membranes, up to 1 nanometer. And if you look to this graph, here you see the kinetic diameters of different gases, and helium is the smallest one, and also hydrogen is very small. A lot of people don't know that water vapor is even smaller than hydrogen. And then you have, for example, CO2, nitrogen, CH4, up to 1 nanometer later, which is the liquid organic hydrogen carriers. So which membrane classes are generally available? So in principle, we can difference polymer membranes, which are applicable in the low temperature area up to 200 degrees C. Then we have the metal membranes, for example, the palladium membrane, somewhere in the range of 300 to 500 degrees C. And I want to focus today on my talk on the ceramic membranes, and there we have the microporous membranes, we have the metal organic frameworks and the zeolites, and we have the ionic conductors, which maybe for the most of you are from the interest here of this talk. So therefore, I made an outline. So in principle, yeah, I want to focus on porous membranes. I want to show some new results of carbon-based membranes developed by a colleague of mine, Tim van Gestel. I have only one slide about the zeolites and the metal organic frameworks, and the second part is more concentrated on oxygen conducting membranes and hydrogen conducting membranes. That means the oxygen and the proton conductors as a dense membrane. So let's start with the applications for porous membranes. And you know, in Germany, we have to switch our energy system. So the last nuclear power plant in Germany was shut down last year. But in addition, there was a decision from the German government to reduce also CO2 emissions. And that means also to reduce fossil power plants. So that means we have to switch very quickly to renewables. And you know always the problem what we have for renewables. If you have a lot of wind and sun, we have a lot of energy available, we have to store it. And if we have no wind and no sun, we have to use the stored material. And then hydrogen is one resource, what is very important also as a renewable fuel, because it can be made, for example, by electrolysis or also by renewables. And then I want to show here two possible applications for porous membranes. So one is extraction of CO2 from flue gases, for example, from a cement plant. We have here one running project with Herion. They focus on polymer membranes, and the colleagues from Herion asked us, can you also make membranes from ceramic, which enables to separate CO2? I have to mention that in the temperature range from 0 between 200 degrees C, it is very hard for a ceramic membrane to compete with a polymeric membrane because they are some orders of magnitude cheaper than the ceramic membrane. So maybe the application for us are more focused on this high temperature area, but nevertheless, I will also here look to the CO2 separation from flue gases, because sometimes the environment is very harsh and then a ceramic membrane can have maybe some advantages. Another idea which we catched up, for example, from ThyssenKrupp here in Germany, the question is how we can supply a hydrogen to households. And there was one idea, maybe we can use the pipelines of natural gas, which are existing in Germany. And maybe we can add to this pipeline 15% hydrogen to transport it. But then the question is how to separate this hydrogen at the end of the pipes, and then maybe a porous membrane can be used also for this. But there are also some other applications which are very interesting. I apologize for the next slide because it's partially in German. I took it from the internet. That is another separation task, which is maybe very interesting for the separation of liquid organic hydrogen carriers and hydrogen. That means that is a solution which can absorb a lot of hydrogen. And then you can use it for storage of hydrogen, and when you need the hydrogen, you have to make a pressure swing, and then maybe you have to separate the LOHC gas from the hydrogen. And maybe also a membrane is very interesting here, because the pore size of this liquid organic, the molecular size of this liquid organic hydrogen carriers is up to 1 nanometer. And if you compare it with hydrogen, which is below 0.3 nanometer, that means maybe we can use already existing membranes for the separation of hydrogen here from this liquid organic hydrogen carriers. But also the separation from water and alcohols is a very interesting application, or from CO2 and hydrogen, or CO2 and CH4, or H2 and CH4. So in principle, there are various possibilities for application of porous membranes. So what is known? So now I want to start with the old stuff. In principle, when you look to literature and you look to a microporous membrane, you find some silica membranes. The silica membranes has amorphous network, and in principle, the name microporous is completely wrong, because we don't have any pores here, because it's in principle a free volume in an amorphous network, which has exactly the size which we need for separation of hydrogen and CO2. But pure silica is very quick, has a very quick degradation in humid conditions, which we mainly have here. And for this reason, it is stabilized by some carbon in the lattice. That means we can open the network a little bit. That means to make this open volume a little bit bigger. But in addition, it is then hydrophobic, more hydrophobic than hydrophilic. And another option of the silica membranes are carbon-based membranes for hydrogen separation. Here it is also not a pore. Normally that are graphene layers or graphite layers, which have a distance between the layers, which is also in the range of 0.3 nanometer, which enables the separation of hydrogen from other gases. And that is in principle 2 types, which are already published. If you look to the structure of such a membrane, normally you start with a commercial disc. You can buy it in a lot of companies. The discs are mainly by alpha aluminium oxide. You can find it as a disc or as a tube. For a tube, mainly the inner side is then coated with the membrane layers. So that means the structure of such a membrane looks like this. So you have here the support. The pore size differs from 50 nanometers up to a few micrometers, depends where you buy the support. And then you need, before you make the microporous membrane on top, some intermediate layers to decrease the pore size. And in the past, it was used gamma aluminium oxide, but that is also not very stable in humid conditions, and in the recent years it was changed to 8YSZ membranes with pore sizes of 5 to 3 nanometers, and these membranes up to here are commercially available currently. So the question is now, when we want to separate gases, we have to add this hydrogen selective membrane layers. What I already showed can be a silica or a graphene. But one problem of this existing graphene layers is they are sticking very well to the support, but sometimes after application, you can see it here, it was tested at 5 bar and 200 degrees C, and then if you remove then the polymeric sealing from the membrane, you have here on the edges a delamination, especially when water is in the atmosphere. That means the attachment of the membrane to the layers, to the support layers and the intermediate layers is good, but not good enough, especially in water. And then my colleague, Tim van Gestel, was thinking how I can increase this attachment of the membrane to my support layer, which is here, the intermediate layer zirconia with 5 nanometer pore size. And here you see the graphene laminate. So, and one idea he catched from literature from our colleagues at MIT. And this colleagues was in the presentation focused on making some glues. And they looked to nature, to muscles, and the question was how this muscle attached to a stone, and also you see underwater that this attachment here is very strong. And in this literature, you can see that they use this muscles use a super glue, and this super glue is a kind of dopamine, which is also in our body. Dopamine is something, for example, what our body produces when we make sports or when we feel happy, but it is also a super glue which the muscles here use. And what is very interesting, so this super glue is hardening underwater, and also it is very fast under dynamic conditions. So the question is how we can use this idea from the glue development here for our membranes. So, and yeah, what we did then is we made in principle a solution, a water-based solution. We took here dopamine from the muscles. So from this bio-inspiring, we mixed it into our water. We have also a buffer inside, and then we heavily stirred it and took first our planar supports into this liquid. And then we can see that the reaction starts immediately after a few minutes. And after 20 minutes, you have a gray layer. And after 60 minutes, you have a big black graphene dopamine layer on the surface. And the first idea was to coat our membrane with this dopamine to improve the performance, to improve the attachment of this membrane layer to the support. Yeah, and then we did in a second step a firing of this layer. So we transferred in principle by different steps in the furnace this dopamine also to a carbon layer on top of this graphene layer. And it looks very nice. So it has a very good structure without failures. And when we make then a gas performance test, and I have to mention that it is a single gas test, then we could observe that at a temperature of 200 bar, CO2, nitrogen, and CH4 could not pass the membrane. So that means our layers are in the range of the desired diameter. But helium and hydrogen, for example, could pass the layer. And we can also see we made here different kinds of membranes. So the pure graphene layer is here, the gray bullets, and the black layer is a graphene layer, which we coated on top with a polydopamine layer. And then we tested also again without any graphene, the converted polydopamine layer. And then we saw that it was much better than the graphene layer. So that means when we use a polydopamine membrane, we don't need any graphene layer on top. And then the question was how the attachment looks like to the support. And we looked to literature, and there was no classified tests. So we had an idea. We go to our workshop, to our colleagues there, and we said to him, please give us the most sticky band you have in the workshop. And then we put this band on top of the membranes, and then we removed it again. And here you can see the result. So when we have only the graphene layer, it is still on the band here after removing. So it is destroyed, the layer, and that is the polydopamine layer with the graphene membrane. You don't see any attachment to this sticky band. And also if we have only the polydopamine layer, there was no delamination, or it was still on the support. So it is a very sticky material. And also the performance looked very good. So the next step is now to test here it in mixed gases and also in humid conditions. And also we want to know how the microstructure of this membrane looks like, because we are sure that it is not a similar microstructure like a graphene layer. We ask now for some temp measurements, and we are waiting for this, and hopefully in a few weeks we can show you then also the microstructure. And then we want also to prepare here a new paper about all these results, which are currently not published. So regarding the temperature range where we can applicable, well, these membranes are applicable, we made also a test between room temperature and 200 degrees C. And what we can observe here, that at low temperatures, in principle, we have not a good separation factor. But by increasing the temperature, we guess that also the distance between the layers or the rings increases, and then we have some, in principle, flux of helium and hydrogen, but still a very low amount of flux of CO2, nitrogen, and CH4. So that we were able to make separation factors between 40 and 100 between the different gases. You can maybe now ask why the separation is lower in the polymethamine, but it is quite similar. The performance here of CO2 flux is very low, and only in principle, yeah, this what is transported here from CO2 depends the separation factor and not the large amount of hydrogen and helium what is passing here. So I have to mention also that we have here running a very large project in Germany, coordinated by our colleagues from the polymer membranes in Herion, which is also a Helmholtz organization coordinated by Thorsten Brinkmann. And the idea is here to test the membrane modules on a on a flue gas in a cement plant at ThyssenKrupp Polysius in Beckum. That means we want to install here a few square meters of polymer membranes in the flue gas stream of this plant, and look how much CO2 we can separate. And in addition, we will also test a small module from half a square meter or up to 1 square meter from the ceramic membranes. In addition, we look to hydrogen separation, which is more on focus for our graphene membranes, for example. We worked with Dillinger Hütte, which is a steel manufacturing plant, and the idea from them is how we can remove hydrogen from CO2 and CO containing gases to use it then for the firing for the steel manufacturing. This project is running, and here are some results. So we have here a module, and in the final step, we have here 100 tubes. The tubes are between 10 and 25 centimeters. In this case here, 25 centimeters. And you cannot see the coating because the coating is on the inner side of the tubes. That means a carbon layer, and hopefully we can demonstrate here later also in the large module that we are able to separate hydrogen, for example, from these gases. We tested the single tubes. They are working, but we have to test it now in the real application if these membranes are working there. And also here we use then the pyrrolized polydopamine layer. So that means the carbon layer. And I already mentioned here, you see a SEM picture, how it looks like. We have the porous support here. We have the two zirconia layers. And then on top here, we have the polydopamine layer. A little bit the problem was that in the previous tests, we used a membrane from a Dutch manufacturer. And the pore size of the support is here 18 nanometers. The commercial support we use here from ATEC is in the range of 1 up to 2-3 micrometer pore size. That means we have to make here also some more intermediate or thicker intermediate layers before we coat the membrane on top of it. So only one word to the, you can do it by such a graphene membrane or silica membrane. Also in literature, if you look, you find some options about zeolites or metallic organic frameworks. We didn't work in this field up to last year. And then we have a young researcher, Marie-Alix Pizzucaro, from Twente. I wrote the name wrong. Here's one C missing. And Mrs. Pizzucaro got a young researcher group funded by the German Ministry of Research. And we want to make now also membranes from this metal organic frameworks and zeolites. So the channels are very well adjusted to gas separation. The problem we have here more is that we need oriented pore channels without any defects. And that is currently the challenge which is forcing here this activity. But also here we want to look to similar separations. So for example, hydrogen and CO2 by molecular sieving. Yeah, now let's switch from the porous membranes to the dense membranes. I will not talk about the molten carbonates, but some things about the dense ionic conductors. So in principle, we have two different applications for the dense membranes. One, for example, is the pure gas separation. And we started a lot of years ago for separation of CO2 from power plants. And we could realize this by oxy-fuel combustion. But the problem is you need here a large amount of membrane surface. And that is maybe a little bit too hard for application of such an oxygen conducting membrane. But also in other industries, pure oxygen or hydrogen is needed, and therefore you can in principle use such ionic conductors. If you have on one or both sides of the membrane a chemical reaction, in addition, we call it a membrane reactor. And then we find several applications from CO2 utilization to the production of commodity chemicals, chemical energy carriers. And that is the focus now on my next part of this presentations. So when we started this activity in 2017, we first made a literature study. So the question is, if you have a separation ionic conductor membrane, which applications are possible? And then that is all what we found in literature, and that makes it is not clear that all this separation task really makes sense from a commercial point or scientific point. But that is this separation task we could find in literature. And the blue parts are by oxygen transport membranes realized, and the green parts by proton conductors. And you see here also some things like ammonia synthesis, or maybe also the decomposition of ammonia. You can use membranes, but also the production of syngas or hydrocarbons. And then we had to take a decision on which part we want to focus. And then we thought, yeah, okay, you know this from literature here. You have this graph from Sundmacher et al. From 2005, and it shows the application mode of such an ionic conductor. You see the electrolyzer mode and the fuel side mode, where, for example, I²CNER is also have a lot of work. You have also the ionic pump, and all this is driven by an outer voltage. But then if you look to this point here, I lim, you have one point where you have no outer voltage, but in this case, you need the mixed conducting membranes, which is able to transport oxygen ions, but also which have some electronic conductivity for electrons. And one possible application, what you find in literature, and I guess here in this field is the most literature available, is the partial oxidation of methane, where you want, you have on one side air, you split the oxygen to an ion, transport it to the membrane, and it partially reacts with the methane for production of a syngas. So in principle, you have here two different systems of membrane reactors. On the left side, what I already explained is a partial oxidation of methane, what is called a distribution reactor, because in this kind, the oxygen is distributed to the gas where it has to react with. And on the other side, for example, for the water gas shift reaction and the separation of hydrogen, it is so-called extraction reactor, because you extract the hydrogen from an existing gas mixture. And that are maybe not the most relevant, but they are the most easiest to explain and also maybe to build. And that is why we decided to start with these two applications to develop it. And the question is now, what are advantages and disadvantages of electrical driven and chemical potential driven systems? Because here the driving force is not the outer voltage. It is in principle the gradient of the partial pressure or the chemical potential of the gases on both sides of the membrane. And the advantages of the electrical driven systems is it is easier to operate by changing the voltage. It is already a high TRL level reached. What I said, the transport is electricity and partial pressure gradient driven by this. But you need a more complicated construction. You need, for example, also conductive housing materials, and that is often a problem. Because a colleague of mine published also recently that 90% of the material cost of an SOFC stack lies in the material of the interconnect plates. And that is in principle much better for the chemical potential driven system. The operation is more complicated, is a lower TRL, but it is an easier design, and maybe you can decide for a non-conductive, very cheap steel, or also ceramic is possible here to use it as a stack. And yeah, the question always is, what is the best material for membranes? What is the best design? And when I talk with the students, there is only one answer which is correct. It depends always on application. You have to look first which application you want to use the membrane, and then you can see what is the best material and what is the best design to applicate this membrane. And here in Jülich, we work on different material systems related to the different applications. For example, a lot of you know very well membranes from lanthanum strontium iron cobaltite perovskite LSCF, or from strontium iron-based STF material. And we are able to make by tape casting, for example, membrane layers here in the range of 20 to 30 micrometer in size, gas tight. We measure this by a helium leak test. But also dual phase membranes may be sometimes from interest, because here you can separate between an electron conducting phase, which is, for example, an iron cobalt spinel layer, and gadolinium oxide, which is a very good oxygen conductor. Then you need these pathways to ensure that you have everywhere conductivity. And also for proton conductors, you have the conventional systems, which are also always shown by our colleagues from I²CNER, for example, BCZY, that is a perovskite on the barium zirconate or cerate level, or for fuel cells here. But also we have some mixed conductors like lanthanum tungstate. We're able to manufacture this by tape casting. So how such an oxygen transport membrane works? So in principle, you have the dense membrane here. You split the oxygen to an ion, and on the other side, then in principle, it reacts with the gas. And there are some advantages. The application temperature is 800 degrees C. And yeah, and then the question is how we can increase the performance of such a membrane. Yeah, and then we made a model, because if you look to literature, the people always looking to the materials, and then they say we have a BSCF, and that is a well-performing material. It has fluxes from 10 milliliter to 20 milliliters per square centimeter in minute, and not like STF, which is maybe only it is below 1 milliliter, and then they decide very quick BSCF is the best material. But BSCF is not stable in CO2 containing environment, and STF, so the strontium-based material, is stable, but it has a bad flux in low partial pressure gradients. But if you put it in a membrane reactor where you have a high driving force. For example, on one side you have methane with a partial pressure of 10 to minus 20. On the other side you have air, which 0.21 partial pressure. And then you have in principle a large driving force. And then the most people said, let's increase the material or the thickness of the membrane, because already Hanne Baumeister showed that in principle, if you reduce the thickness, we can in principle increase the performance, but that is also not completely correct. And we had now a recent PhD work, which is maybe ready. It is ready and it is currently in the printing phase. And here we demonstrate that not always the material or the thin film is determining the flux, because if you have, for example, BSCF, the flux of the material and the surface reactions are so fast that the support here is a limiting step. That means we have to work also here on a low tortuosity. We have to work on pore sizes in the range of several micrometers. And also we have to develop a thin support. And it depends on the material which layer here is the limiting step for the transport. And that can be the support, that can be the surface reactions, but it can also be the material or the thickness of the membrane. And that is what my colleague, I don't have now detailed results, but if you're interested, you can contact me. And I guess in a few weeks, there is a complete PhD thesis available, unfortunately, in German language. But we will also write a publication from it where we show exactly how the transport properties is working in such an asymmetric design, and what we have to do to increase the performance of such an asymmetric structure. So we produce it here by tape casting. I have at university a complete teaching course only about manufacturing, but in this lecture I don't want to focus on it. Here we show different materials which we was managed to make here with different support structures. And then the next step is to increase this 15 millimeter membranes to larger size. That means what is interest for later maybe commercial applications, and then we scaled up first to 10 by 10 centimeter. That is in this case, for example, an LSCF or an BSCF membrane with a different membrane design. And if you use then the same temperature and sintering program, like for the 50 millimeters, you produce only rubbish. It is completely destroyed, the membrane. And the reason for this is you have here a larger volume of membrane which you have to sinter. And what is shown here on the picture, on the DTA and TGA curve on the right side, that the limiting step for the firing is a low temperature area, because below 100 degrees C, first we have to remove the residual solvents, and the plastifiers are melt and has to be pyrolyzed. And if you do this too fast in this temperature range, your structure of the large membrane is completely destroyed. That means we have to work here with very slow heating rates and also with some ramps. And then once everything of this organic is removed, we can go faster to higher temperature, to our final sintering temperature, which is, for example, for BSCF 1100 degrees C. For LSCF, it's in the range of 1150 to 1200 degrees C. Or if you now look to the barium zirconates, where Pati is working with, you can also find temperatures from up to 1700 degrees C. So also here, it depends on the material. And then the next step is what we plan to do here is this year, we want to bring one reactor in operation and to demonstrate that the partial oxidation of methane with such a mixed conducting membrane is possible. And then the first question was, which material we want to select for this reaction. And so we have a very high driving force in this reactor, but we need a very stable material in a very harsh condition, including CO2 and maybe some SOx in the gases. And then we decided to go for an STF25, so a strontium titanate-based material, which has under this conditions also reasonable performance, which can be compared with LSCF. And then we use our SOFC design, what we have already here. We modified a little bit. Then the next challenge is to seal the membranes into the housing. And then we produced such a first two-layer reactor type. And this reactor is now ready and waiting for testing. So we have to wait until our SOFC rig is free, and then we want to test it for the partial oxidation of methane till the end of the year. And hopefully then I can demonstrate you that it is working. But people which are working on stacking, you know, there are always some problems, sometimes with the sealing or sometimes the membrane cracks or other problems which can be occur. And that is what we have to take now into account, how to operate such a stack for a long time. We already managed it for SOFC. We operated one stack with aging rate of 0.8% on 1,000 hours, up to 100,000 hours. So that means more than 10 years, and that is demonstrated, and that is what we also have to the target here in the next year to demonstrate that this partial oxidation of methane is working. So I'm a materials guy, but we have also some colleagues in other institutes in the former I²14. They have now also a new name. I guess they are now ITE2. And they, for example, calculated the desired reaction here, the partial oxidation of methane, and then you can, in principle, calculate how many methane you have when you have a flux rate of the membrane, how many oxygen is permeating to it. And then, in principle, we need exactly this ratio from CH4 to O2 from 2. Then we have, in principle, a methane conversion rate of 95% and a very high selectivity of 97%. And and that is what we are also doing here. So we look to the complete system with 5 different institutes here in Jülich. And our part here in this project is to increase, in principle, the size of the membranes. And now I have not so much time left. I have to be a little bit quicker. CO2 water splitting is one option. So we have one project with DLR, where we want to use the solar heat from a solar reactor. And also in a new project, we want to build a membrane reactor system for CO2 decomposition in a temperature range of 1500 degrees C. And here for sure you need a tubular membrane. A planar system is not good anymore. Now I have to be quick. We have another project on the proton conductors with our Spanish colleagues from CSIC and University of Valencia. The idea is to make a hydrogen separation layer where we can remove hydrogen from, for example, ammonia or other fuels to use it then in a combustion system of a ship or a train. And here we started with some cells of barium zirconate, cerate electrolyte layer. Also a lot of other organizations like SINTEF, DTU, I²CNER, and University of Twente has here some development. And also we here work very close together with Professor Ishihara and Matsumoto and Kwati. And Kwati is currently 10 months here. He produced some cells here in Jülich. One problem is the sintering. Here you see, for example, how the sintering happens for a 15 millimeter membrane. First, the thin film on top shrinks, then the support is shrinking, and you have then to create, by this knowledge, a sintering program where your membrane is flat at the end. And and also we want to know here, we did it together with another unit here in Jülich, how the in principle chemical composition looks like in the electrolyte. And then Kwati gave this to this institution. We made a FIP lamella here. We have also the grain boundary, and then you can see here how the distribution of the nickel, that it is enriched here, for example, on the grain boundaries, that we have also an yttrium-rich phase. And here Kwati already, I guess, wrote a publication which is currently under the process of reviewing. And he has also very nice results with his cells. This is measured in Kyushu. He was managed also to reach very high current densities. So last but not least, I maybe need 5 more minutes if this is okay. I want to show another project which we have together with BASF, WZR, Shell, and some other companies. And the idea is here the dehydrogenation of ethylene, of ethane to ethylene. And for chemical applications, we have a project here together with our colleagues from Netherlands. And we want to use first of here a mixed conductor. So we built a reactor at BASF and HTE, which is a daughter company from BASF. We made some membranes from lanthanum tungstate. We measured here the separation. And also we look here to additive manufacturing. Additive manufacturing means we look not only to tape casting, we look to binder jetting, material extrusion, 3D printing, and material jetting. And we tested these membranes and we were able to produce them together with our colleagues from WZR to seal them in a metallic housing and to test them in the test reactor. On the right side here, you see the tape casted sample. And then the idea was, how we can make it also with this additive manufacturing. And now I'm at the end of my presentation because the time is up. I have some remarks and conclusions from my side. There are a lot of new application options in separation tasks in the production of synthetic fuels and chemicals. Be open to these new applications. Be flexible in membrane designs. Tubular or membrane can be benefit. It depends always on application, like also the material selection. Do not focus only on world record and performance, what a lot of groups do. Look also how that it is stable under operation conditions. The microstructure has a very important property if you want to come to good performances. We need projects with higher TRLs. We need industrial contribution. And the last sentence I want to close with, together we are strong. Strengthen the outcome of science with national and international collaborations. And that's my group currently. And thank you for your application, for your attention here.
Oh, thank you very, very much, Willie, for this very, very nice presentation. I guess you will be receiving many questions from this talk. And
yes,
so,
sorry, I closed my presentation, but it's maybe not needed. Otherwise, I will
yes.
open it again. Yeah.
Yes. So the
okay.
So the presentation is now open for discussion. Please, if you have any question, you could just indicate by a raise of hand on the panel there. So do we have any questions from the talk? Yes, we also have a group here who is there's a group here which is also very, very active in membranes development.
Yes.
Yes, I think so. There's a group. Let's start with. I think there's a hand. There's a show of hands here. Okay, please go ahead. I think this is.
Hello.
Hello, please. Can you go ahead?
Yes, I can hear you.
Okay, my question is a little bit. Thank you very much for the talk. My question is a little bit technical.
Yeah.
I found that in the beginning of your presentation, you were using a large pore support like 50 nanometer or something like that, and then you are using some small pore material inside that. Why cannot you use the small pore stuff directly? Why you need a large pore?
Yeah. It differs to the application.
Okay.
So for the first part from the microporous membranes, we have two suppliers. One is Pervatec, and Pervatec supplies supports with 80 nanometers in size. These membranes are very well working, but very expensive. And we have also membranes from Artech, and the price of these Artech membranes is one order of magnitude lower, so a factor of 10.
Okay.
But they have pore sizes in the range of 1 to 2 micrometers. So when you now want to applicate a membrane layer of maybe a few nanometers in size or 100 nanometers in size on top of this membrane, and you have pores of 1 micrometer, you will fail. That means when you start with a lower pore size, you need much less layers than if you start with a larger pore size. From the other side, if you have larger pores in the support, you have a higher gas flux. What you also have to take in account, because the small pores in the support are blocking the gas, and then maybe what happens, for example, in the oxygen transport membrane, sometimes if the pore size is too low, that means only a few micrometers. So here we need larger pores, and you have a so-called polarization effect. The oxygen permeates to the membrane, but the nitrogen cannot permeate. It stays on the surface, and then it kills your gradient of partial pressure. That means we have always to look to the pore size, what is possible for manufacturing, and the second thing is for which application we do need it. So for some application, we really need larger pore size in the supports, and for other ones, the smaller are better. And that depends, So in principle, you have both options with advantages and disadvantages. Is that question answered?
Yeah. Thank you.
Okay. Okay. Thank you very much. The next question, I think, is Professor Hudo. Hudo Sensor, please, can you?
Can you hear me?
Yes, very well.
Okay, thank you for your nice talk today. I'm also working on the proton conducting ceramic fuel cells. Then
that's great.
Yes, but my cell is very small compared to yours. So then I would like to make the bigger cell. So what is the most influential factors to controlling the bending of the cell? I always, my cell is always bending. So what is the most important factors to control it?
So the proton conducting cells are the most difficult issue for manufacturing. And that has different reasons. One reason is, I guess you will work also with a barium zirconate cerate electrolyte, right?
Yep. Yes.
Yeah. And
True.
the problem is that this, for example, the barium zirconate has a very high firing temperature. If you fire it only without any sintering aid, you end up with firing temperatures 1600, 1700 degrees C. And for this reason, a lot of groups add, for example, a little bit nickel up to 0.5%, or also, for example, John Irvine uses zinc. Then your performance is a little bit lower, but it's easier to sinter. And the sintering of these cells is really an issue. And also, we made flat cells, but it works not every time. And Quarti had an excellent idea, which is not written so much in literature. So in principle, when you use a support, you take also a barium cerate zirconate support, which has also a very high firing temperature. But Quarti, for example, has also a strontium-based support. And if you use this support, you have a much higher shrinkage rate in your support at much lower temperatures. That means you are able to make the layer gas tight, and you can go to a much lower firing temperature. I have to mention that this material is a little bit less stable, but for the sintering, it makes a lot of things easy. And maybe for some applications, and when I think about a fuel cell where you have not so many different chemicals on both sides, maybe this is a very good solution, what Quarti proposed and developed here in Jülich to this strontium-based cell. But that is the main challenge of proton conductors. It's not the material. When you look the last 30, 20 years, always the same materials are used. But upscaling and also making small cells is still a challenge.
Okay.
Yeah, and I showed one picture with a proton conducting cell, also made by Quarti. You have to make first this optical, let's say, dilatometry.
Okay.
And then you can see what is the behavior of the bending. And then by knowing this, you can maybe avoid bending. Also working with round cells, it's maybe sometimes easier this than when you have a rectangular shape, because then on the edges you have also differences. When you make it by tape cast, sorry to say so many things, but there are so many issues that you have to take in account. Maybe the density of your support is also not, or is not on every place the same. If it is not homogeneous, then you have also problems of bending. So there are a lot of things you have to take in account.
I see. Okay, it's very complicated. Just one
It's the most
phenomena, but,
complicated.
there
It's
are...
not to compare with an
Okay.
oxygen transport membrane,
I
which
see.
is much easier.
Okay, I see. Thank you so much.
Yeah.
So are there any other questions? I was curious if Professor Ishihara is now joining.
Maybe one more answer to the former colleague.
Okay, yeah, you can go
Some
ahead.
groups like
So,
DTU, for example, work also for this reason with symmetric cells, what helps also the bending to avoid a little bit bending. Yeah,
I see.
but
then
that
one-time
has,
evaporation after the sintering process.
yeah.
Okay, I see. Is this effective for the actual manufacturing process? Can this method use for the manufacturing line?
Yeah, the manufacturing is, yeah, you can also use here a lot of different methods. And also we use here tape casting, not because it's maybe the best method. The people say always the best method is the method I'm using, yeah. And we have a lot of knowledge in this tape casting, and therefore we use this tape casting system. But in principle, there are also a lot of other manufacturing issues which you can use. For example, also the additive manufacturing or screen printing or PVD or whatever is possible, yeah.
Okay, I see.
Okay, we still have a couple of minutes. Is there any other question? Was hoping that Professor Ishihara will come in, but it seems as if he's not there. Then I want to give Professor Kubota Sensei, who is present, to probably say a couple of words and then closing remarks. Kubota Sensei.
Me? Thank you for giving me this opportunity. I really enjoyed your presentation, but I'm not familiar with your research theme, but it was very exciting. So thank you very much for your contribution to the I²CNER webinar. So
it was a great pleasure for me. Thank you.
Thank you very much. We will have, I hope we have collaboration in the future. Thank you very much.
Yeah, so when you want to contact me, Kwati has my email address. You can find me also in internet. Let me know.
Yes.
And we can also have separate video conferences if you want to discuss with me, maybe after vacation time. But I'm in principle available.
Okay, thank you very much. So thank you very much. So bye-bye.
Okay. So
thank you very much to all of you for listening.
Thank you again for coming, and I think at this point we will stop the webinar.